Okay, this is Dr. D. Govardhan, a professor and dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Here today we are discussing electrical analogy for convection and radiation process in heat and mass transfer subject. Convection process. The convection process generally takes place in liquids as well as the gases. That is, the heat energy flows in liquids as well as gases generally follow the convection process. The amount of heat energy that is flowing in convection process depends upon the H value, that is the coefficient of convective process, temperature difference, and the surface area. So the heat transfer from the hot fluid to the fluid surface to the surface of having cold fluid is known as the air convection process, which can be expressed as Q is equal to H into A into T1 minus T2, where Q is representing the magnitude of heat energy that is flowing or heat flow in convection process, which is proportional to the H, that is known as the coefficient of convective, and A is the surface area, T1 minus T2 is the temperature of hot fluid to the cold fluid. Okay, from this relationship we are having here now, the quantity 1 by HA in this case now, it can be written as now T1 minus T2 divided by 1 by HA. This 1 by HA is known as convection resistance to the heat flow, which is equal to the resistance in the electrical circuits. So just when I am keeping the object here now, the heat energy is flowing here now from one region to another region in gases or the liquids. That is here as in just T1 is representing the temperature at one region and T2 is representing the region other one. The heat energy is flowing from T1 to T2, which is given by the equations now T1 minus T2 divided by 1 by HA now. 1 by HA is called here thermal resistance. When comparing, when you are putting in the form of electrical circuits, here T1 is representing the higher temperature, T2 is representing the lower temperature. Heat energy is flowing here now from higher temperature to lower temperature. Here 1 by HA is called thermal resistance now. When you are putting this same thing in the electrical circuits, here electrical circuits, here it is nothing but represented like this, assume. Here it is equal to V1 is representing the voltage at electrical potential at one end, and E2 is the electrical potential at the other end. I is that is the current which is passing through E2, and R is the electrical resistance. That is, when you are just comparing these two, the V1, V2 are the equivalent to T1 and T2, and current flowing now, thermal energy flowing, that is I and Q both are equivalent. The R is the here electrical resistance, 1 by HA is representing the thermal resistance of convection process. Here based on convection process, one problem is determine the heat transfer by convection over a surface of 0.5 meter square area if the surface is 160 degrees centigrade and fluid is at 40 degrees centigrade. The value of convective heat transfer coefficient is 25 watts per meter square per degree Kelvin. Also estimate the temperature gradient at the surface given K is equal to 1 watts per meter per degree Kelvin. The given data is equal to H is equal to 25 watts per meter square per degree Kelvin. A is equal to 0.5 meters square now. T1 is equal to 160 degrees centigrade and T2 is equal to 40 degree centigrade. Okay, by using the equations Q is equal to HA T1 minus T2, that is the amount of heat energy that is flowing in a fluid is given by HA T1 minus T2, where HA is the coefficient of heat transfer coefficient, A is the surface area, By substituting these values in these equations, 25 into 0.5 into T1 minus T2 is equal to 160 minus 40, which is equal to 1500 watts or 1.5 kilowatts. The thermal resistance is equal to 1 by HA, equal to 1 by H is equal to here 25, A equal to 0.5, which is equal to 0.08 degrees centigrade per watts. The fluid has conductivity here 1 watt per meter per degree Kelvin. Okay, according to the equations now, Q is equal to minus of Ka into dt by dx. The temperature gradient is given by dt by dy is equal to minus of Q divided by Ka. That means by using this relationship, Q is equal to minus of Ka into dt divided by dx. By using this relationship, dt by dx is equal to minus of Q divided by Ka. From this relationship, we got the temperature gradient is equal to minus of 3000 degrees centigrade per meter. The radiation process. The heat energy flows from one object to another object, which are separated by far distance and not having any physical contact, they are separated by longer distance. The heat energy flows by using radiation process. In this case, due to the electrical and radiation process, the thermal radiation is a part of the electromagnetic spectrum in the limited wavelength, range of 0.1 to 40 micrometers, and emitted all the surfaces irrespective of temperature. Such a radiation on the surface is observed, and thus radiation heat transfer takes place between the surfaces at a different temperature. And no medium is required for radioactive transfer. Here we are taking the object A is there now, A2. T1 is the temperature of the first object, T2 is representing the temperature at second object now. Since when the body is exposed to higher temperature, the energy is emitted by A, it will emitted in all the directions now. And similarly, A2 is also exposed to T2, it is also emitted certain heat energy from its surfaces. So the net amount of heat energy that is flowing, it depends upon the temperature differences of two objects which is at T1 and T2 respectively. Okay, according to the Stephen-Boltzmann's law, the net amount of heat energy that is flowing from body which is at higher temperature to a body lower temperature is given by the equations F into sigma into A, T1 to the power of 4 minus T2 to the power of 4. Where F is the shape factor, sigma is the Stephen-Boltzmann constant, which is equal to 5.6 into 10 to the power of minus 8, and T1 is representing the temperature at higher temperature, and T2 is the temperature of the body or the regions at lower temperature. So the amount of heat energy is given by Q is equal to F into sigma into A, T1 to the power of 4 minus T to the power of 4, and substituting the values in this equation we got now. Here T1 to the power of 4 minus T to the power of 4 divided by 1 by F into sigma into A now. Or it can be modified as T1 minus T2 divided by 1 by F into sigma A and divided by A now, multiplied by T1 plus T2 into T1 square plus T2 square and so on now. Where the denominator is referred as the radiation resistance which is equal to the current flowing from the higher potential to the lower potential. So here now T1 is representing the temperature at higher body, T2 is the temperature of the lower body. The heat energy flowing from T1 to T2, assume Q is the thermal energy that is flowing. Here thermal resistance is given by 1 by F into sigma into A1, T1 plus T2 into T1 square plus T2 square now. So this value is nothing but obtained by using the relations now. T1 to the power of 4 minus T2 to the power of 4, it is given. It is in the form of A square minus B square, which is equal to T1 square minus T2 square into T2 square plus T1 square plus T2 square, which is also equal to T1 plus T2 into T1 minus T2 divided by T1 square plus T2 square now. From this relation, we required T1 minus T2 at the top we are taken now numerator, the remaining value in the denominator. The determination of F values are available for simple correction in the form of charts and tables, but generally for the block surfaces, when the surfaces are parallel to each other, it is equal to 1 here. Now, based on that is the radiation process, we are taking one problem. A surface is at 200 degrees centigrade as an area of 2 meters square. It exchanges heat with another surface B at 30 degrees centigrade by radiation. The value of factor due to the geometric location and emissivity is 0.46. Determine the heat exchange and also find the value of thermal resistance and the equivalent convection coefficient. So the given data in the problem is the T1 is representing the temperature of the body, which is having higher temperature, which is equal to 200 degrees centigrade. When we are converting into degree of Kelvin, 200 plus 273 is equal to 473 degree Kelvin. T is equal to 30 degrees centigrade, which is equal to 30 plus 273 equal to 393 degrees. Sigma is equal to, that is Stephen Boltzmann constant, which is equal to 5.67 into 10 to the power of minus 8. A is the area of the cross section, which is equal to 2 meter square now. F is equal to, that is shape factor, which is equal to 0.46. Okay, and substituting the values in that equation we got, the amount of heat energy flowing is given by Q is equal to 0.46 into 5.67 to 10 to the power of minus 8 into 2 into 473 to the power of 4 minus of 393 to the power of 4 now. And simplification we got to Q is equal to 2171.4 watts. So the resistance can be found by using the relationship Q is equal to delta T by R now. Delta T is a change in temperature, which is equal to 200 minus 30 divided by Q is equal to amount of heat energy that is flowing, which is equal to 2171.4. From this relationship we got to R is equal to 0.07829 degrees centigrade per watt. Here another problem. A surface is 200 degrees centigrade and it is exposed to surroundings at 60 degrees centigrade and converts and radiation heat to the surroundings. The convection of coefficient is 80 watts per meter square per degree Kelvin. The radiation factor is 1. If the heat is conducted to the surface through solid of conductivity 12 watts per meter per degree Kelvin, determine the temperature gradient at the surface in the solid. So the heat conducted through a surface, assume it is having area of cross section is equal to 1 meter square. The heat energy conducted is equal to Q is equal to, it is the sum of the heat energy that is transferred by using convection process as well as the radiation process, which is equal to H into T1 minus T2 plus sigma into T1 to the power of 4 minus T2 to the power of 4 now. Here, this equation here we have taken F is equal to 1 and A is equal to also 1 now. And substituting the values of H is equal to 80, T1 is equal to 200 minus T2 equal to 60 plus 5.67 into 10 to the power of minus 8 into T1 to the power of 4, that means here we are taking 200 plus 273 by converting into Kelvin minus 60 plus 273 is given. From this relationship we got it is equal to 11,200 plus 2140.9. Total is equal to 13,340.9 watts. The temperature gradient is equal to, the equation is equal, Q is equal to, we are having K into A into dt by, here dx is given now. Here from this relation, so we are having A is equal to, already we have taken A is equal to 1 now. From this relation, so K is equal to, the values is given 12 watts per meter per degree Kelvin, A values is given, and so Q is equal to, we are dt by dx, this is called thermal gradient, that is temperature gradient, which is equal to Q divided by K into A now. And substitute the values in this equation, so that is 13,340.9 divided by 12 into 1, so which is equal to minus of 1111.7 degrees centigrade per meter. The problem number 4. Heat is conducted through materials with the temperature gradient of 9000 degree centigrade per meter. The conductivity of the material is 25 watts per meter per degree Kelvin. If this heat is converted to the surroundings at 30 degrees centigrade with the convection coefficient of 345 watts per meter square per degree Kelvin, determine the surface temperature. If the heat is radiated to the surroundings at 30 degrees centigrade, determine the surface temperature. Since the convection and radiations are involved in this case now, so the amount of heat energy that is transferred by using conduction process should be equal to the amount of heat that is transferred through convection process. By considering A is equal to 1, we are having minus of 25 into 1 minus of 900 equal to H is equal to 345 into 1 T1 minus 30. From this relation we got T1 is equal to 682.17 degrees centigrade. In this case, conduction and radiations are involved. The heat conducted is equal to here heat radiated. From this relationship we got minus of 25 into 1 into minus 900 is equal to 5.67 into 10 to the power of minus 8 T1 to the power of 4 minus 306 to the power of 4 now. From this relationship we got T1 is equal to 1412.14 degree Kelvin, or which is also equal to 1139 degree centigrade. This entire information are collected from the textbooks which are given here now, and the reference books also are taken. See Kodandaraman and Holloman heat transfer. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.